Good day. My name is Brian Kelly. I'm Global Applications Engineering Manager at Honeywell Thermal Solutions, and our subject for this video tip today is the effect of altitude on combustion systems. So with the increase in altitude of your plant, process, the combustion system, etc., the density of the air decreases as you go up higher in altitude. So this is going to have an effect on any system that uses low pressure air in the process. So when you look at a total burner system, not only does the burner need to be considered, but the altitude is also going to affect the blower performance, the valve sizing, maybe pipe sizing in the system, possibly depending on what the altitude and the volume is. So the sizing of that blower, maybe even the burner, depending on how much airflow has to go through the burner now, and the pressure of the system is going to affect how that system reacts and needs to be designed. So if we look at a typical burner system, the three main components here that we have to look at are the burner, the air control valve, and the combustion air blower, because those are the things that are handling and flowing that air through the system. So when we look, in this case, at the burner manufacturers are going to generally catalog information, and that flow and pressure data is going to be based on what we call standard conditions, sea level conditions, standard temperature and pressure, STP. So that's used to determine the required burner pressure for the airflow necessary to support the required burner capacity. So in this case, our example for this little tip, this session, is the burner capacity is 8 million V2s an hour. We want to run the burner at 25% excess air, so that's 25% above stoichiometric air-fuel ratio, so perfect combustion. The airflow required for that capacity is going to be a 100,000 SCFH, which is standard cubic feet per hour, and the burner air pressure required to do this is 20 inches water column. This assumes that the natural gas is 1,000 BTUs a cubic foot, and we are at a 10-to-1 stoichiometric air-fuel ratio. So there's our burner. Air control valves and the blowers. So air control valve, I'm not going to go through all this sizing. It's a short video tip. So for 100,000 SCFH we require for this system, we've sized a control valve that's going to take a 3-inch pressure drop at its full open position, which is a good pressure drop to start from. And the combustion air blower is going to be, the flow and pressure required is going to be our 100,000 SCFH, but it's going to be the total of the pressure drops through the system. So we have our pressure drop through the burner, which is 20 inches, 3 inches for the valve. We've calculated 4 inches for the piping. And if you've got an application that has back pressure, you've got to take that into consideration as well. But in this case, we don't have any. So our blower specs are 100,000 SCFH and 27 inches of water column pressure required out of that blower. So what happens when we designed our system and we're moving now that system from sea level to 5,000 feet? Good question, right? So we're at 5,000 feet. We're going to Colorado. So what do we have to do now? We still need to run that system at 8 million BTUs an hour. Nothing's changed about that. And as we stated before, the elevation is going to cause the density to be less. So this affects all the air components in the combustion system. So what happens if we do nothing? We take our system, we size it, we buy everything, and it's for 8 million BTUs an hour at sea level. So what's going to happen is the blower. You're going to have reduced pressure and reduced mass flow volume through the burner. So, and I'll explain that in a second. So the fan laws, which we'll look at in the next slide, are going to tell you the effects of altitude or the density change on pressure flow and horsepower for the blower. In terms of the burner, even if the blower could deliver the same mass flow and pressure, which it can't, if the blower, the burner is going to have a lack of pressure to flow to support 8 million BTUs an hour. So if it even got that 20 inches of pressure, it's not enough mass flow at that point or volume to support the 8 million BTUs an hour, because we've got to move more volume of air through the burner to support the same mass flow. Because we're lighter in air, we get more volume. To move more volume through the burner, we need more pressure to push that increased volume through the burner. So if we look at the fan laws, you'll see them here. So our flow, and Q is mass flow, so consistent units. So the weight flow of air, the pressure, and the horsepower consumed are in direct proportion to the ratio of the densities or the specific gravity. So a blower at sea level or a blower at 5,000 feet is going to move the same volume of air. It's just that we're moving the same volume of air at altitude and it weighs less. So it's less mass flow or less weight of air because that's what we look at as in combustion. We're looking for that SCFH, that referenced flow back to 60 degrees and sea level, 60 degrees Fahrenheit and sea level. So that we know we have enough oxygen to support that, in this case, 8 million BTUs an hour. Um, so if you're not familiar with specific gravity, you'll see the difference in this weight flow. Q is SCFH. Remember that. Is that the density at altitude is less than the density at sea level. So we're going to have a number less than 1. So you'll see that the SCFH flow at the weight flow at altitude is the weight flow at sea level times the specific gravity. So anything above uh, sea level, that specific gravity starts getting lower and lower. And that same relationship goes for pressure and flow, as you see in the formulas above. So when we look at the burner pressure, it's going to need to be corrected or increased to maintain that 100,000 SCFH of airflow required for our 8 million BTUs an hour at 25% excess air and 5,000 foot elevation. So in this case, our pressure required at altitude is going to be our pressure required at sea level, STP, which was our 20 inches, divided by the specific gravity at altitude, which in this case at 5,000 feet is 0.83. So what that tells us is to move the additional volume of air and maintain our 100,000 SCFH, we need to see pressure at that burner inlet, assuming there's no back pressure or other pressures related to the system, of just over 24 inches of water column. So there's our correction. Because if we maintain only 20 inches, we would not get enough volume, I should say, mass flow at altitude to support that 8 million BTUs an hour. So when we come to our blower, again, it's going to be the addition of not only the burner pressure or pressure drop, same thing for a static chamber, our valve pressure drop and any piping losses, and again, application pressure. In this case, our burner delta P is increased to 24.1. Our valve is now 3.6 and our piping is 4.8. This is assuming we didn't change any piping. You may upsize your valve a little bit, but 3.6 isn't too bad. But piping, maybe increase it a size and take that pressure drop back down to 4 or 3 or something like that. So what this gets us to is our airflow, and you'll see our minimum airflow specs, just like at sea level, we require that 100,000 SCFH of weight flow at altitude, and we'll explain that in a little bit. And our pressure now has increased to 32.2 inches versus what we had in the first place. So you can see that makes quite a bit of difference. So when that blower, that altitude correction, so the combustion system at altitude still requires that 100,000 SCFH and that minimum blower pressure of 32.2 to account for all our drops in our pressure or our burner pressure. So the blower's sea level rating and outlet pressure need to be corrected to be able to deliver that required weight flow, SCFH, and outlet pressure at altitude. So it's a pretty simple relationship. Going back to the fan laws, is if we have a blower catalog that we're going to look correct to, and it's based on sea level conditions. If we are figuring for our required airflow rating, catalog rating at sea level, then that sea level rating needs to be 120,500 SCFH. Consequently, the same for the pressure, it needs to be 39 inches, because what's going to happen is when that blower rated at sea level goes to altitude, it's going to be 39 inches now multiplied by our specific gravity, and we'll deliver the 32.2 inches. So we find a blower from a catalog that shows specs of 130,000 SCFH at 41 inches at sea level. So what's going to happen is our mass flow, weight flow, will be reduced to 107,900 SCFH, but it's still moving. That blower is still pushing 130,000 CFH, or actual cubic feet. So volume-wise, it's still moving that air. It just weighs less, so it's less weight flow. This is an important concept for us guys that size burner systems. And what will happen is, just like we said, that 41 inches at sea level is now reduced by the change in specific gravity or density to 34 inches. So that system satisfies our requirement of delivering 100,000 SCFH or 120,500 CFH at the minimum of 32.2. So we have a little more pressure and a little more flow, which is always good in case there's a little rounding error there or something like that. So that comes to the end of my little topic on air altitude. And like I said, don't be one of those guys and say, hey, I know nothing, because you know something now. But it's important fact. And if you ever get in a situation, contact your vendor that handles either fans or your combustion systems to just always be safe, because you don't want to be in a situation that you run down the road and you get that system running and you can't get enough heat. So thank you very much for your time. I appreciate your attention and good luck.